Hi and welcome to Mr. Pi the Maths Guy. In this episode I'd like to look at multiplication and some various aspects of the properties of multiplication and how that translates into the way that we teach it. Now, one of the first things I'd like to look at is what we mean by the multiplication sentence. Quite often you'll see a sentence that might be 3 times 4 and people will think that means 3 lots of 4. When actually it means completely the opposite. It means 3 4 times. So we have the original number is 3 and we want to work out what it would be if we times that by 4. So we would start with 3 and then we'll repeat that 4 times. So we will have 4 columns each with 3 in it. Now you might say, well, this is a bit semantics, it doesn't matter. Well, in a sense, because of some of the rules we're going to look at, you're right. In the end result, it doesn't matter. But from a teaching perspective, it's really good that children are clear what we mean by 3 times 4. So that when we teach it, we should consistently represent 3 times 4 as being 3 4 lots of. Okay, so now we've got that, let's have a look at some of the properties of multiplication. The first property we can look at is what's called commutative property. Now the commutative property almost makes what I said before completely pointless. Although, in a sense, if we didn't establish what a multiplication really means, then there would be no need to have a commutative property, as we would be already saying it doesn't matter which way round you say it. But the commutative property says to us that 3 times 4 is equal to 4 times 3. And in calculation terms, it doesn't matter which way round we do it. Do we calculate it as 4 lots of 3 or 3 lots of 4? As you can see from these arrays, they both equal 12. So they are commutative. That means they can be done either way round. Commutative coming from commute, meaning to move. Now the second property I'd like to look at is called associative. Now associative property is how we group things. And for this example, we need to look at something that has 3 digits in it, or 3 multiplying numbers. So if we look at 2 times 3 times 4, when we look at it in an associative way, that can mean either 2 times 3 times 4, or it can mean 2 times 4 times 3. It doesn't matter which pair of multiplying numbers we start with, the result will always be the same. And again, you can see that from the 2 different arrays, but you'll notice that in both cases they sum to the same value, i.e. 24. Now the final rule or final property of multiplication is what's known as the distributive property. And that simply says that if we are multiplying something by an addition of 2 things together, we can either make the addition first, then multiply the result of that, or we can multiply each element of the addition by the times, and then add the digits together. So as you can see here, we have 2 times 3 add 4, which can be represented as 3 add 4 is 7, so 7 lots of 2. Or we can break it down and say that's 2, 3 lots of, add 2, 4 lots of, again giving us the same value of 14. Okay, so now we've got these properties out of the way, let's look at how we start teaching multiplication. Now for all of these examples, I'm going to use the same calculation, 12 times 3, so that we can see how each of them varies from the previous one. Now when we're first teaching multiplication, the easiest place to start is in what we call the concrete, that is, the real world physical multiplication. And here we look at maybe having 3 sets of 12 items in each set. And as you can see from this example, we've got 12 compare pairs in each of the three sets. So children can go away and count the number of compare bears as 12, then they count another set of 12 and a third set of 12. And then to find the answer, they simply count all of the compare bears to find the answer 36. Now this is an important stage in children's learning of multiplication, the concrete stage. It allows them to physically handle objects that equate to the number sentence. We then would move on from that, away from the physical concrete items to a semi-concrete, where we would use images to replace the physical objects. And as you can see here, again we've created three sets in terms of a drawing, and in each of those sets we have 12 individual items. So again, the children can draw a circle, put 12 items in each of the three circles, and then count all of the individual items within the three circles, and again get to the answer 36. So children are gradually progressing away from physically having to handle things to using pictorial representations, and this is a move towards abstraction, a move away from physical objects. The next stage, we would try to get children to organise those pictorial images into what we call an array. Now an array is simply a way of organising those pictorial representations into something that looks like this. So as you can see here, we end up with the numbers being represented in a rectangular form, or a rectangular array. Each of the columns has 12 items in, and there are 3 columns. So we can see we've got 12 times 3. Now we would also at this stage be helping children to recognise the commutative property that multiplication has. So as you can see here, we have the one array, 12 times 3, but we get children to quickly recognise that that is equal to an array of 3 times 12. So at this time we have columns of 3 and we have 12 of them. Now we start to look at this because it might be that children find doing 3 times 12 easier to do than 12 times 3. After all, it's far easier to count in 3s than it is to count in 12s. Following on from the commutative property of the array, we then move into the distributive property. So we start to get children to recognise that they can partition the number 12 into a 10 add 2. And you can see here that we've created the array with 3 columns of 10 and a further 3 columns of 2. So they can see that it's 10 times 3 add 2 times 3. And this is the first step in getting to children to recognise how we can break a calculation down into smaller components that will make the process easier. This then leads us into how we use a number line, and again we use the partitioning idea of 12 and splitting it into 10 and 2 and saying that we can multiply that as 3 lots of 10 add 2, which we can then split into 3 lots of 10 add 3 lots of 2. And as you can see here on the number line, we have 3 jumps each of value 10, followed by 3 smaller jumps of value 2. Now this will be important that children recognise that each jump is 10 and each of the subsequent jumps is 2, but it will quickly lead to children who are really grasping the idea of recognising that the 3 jumps of 10 can be simply repeated as 1 jump of 30, knowing that 3 lots of 10 is in fact 30. And again 3 lots of 2 is 6, so they will simply do 1 jump of 30 and 1 jump of 6 to get their answer 36. But this is about children making that connection, and it needs to be a step-by-step process. Following on from the number line, we then use this notion of distributive property of multiplication to start moving into a more formalised way of doing the multiplication, and this is in the form of a grid method. where you can see here that we've taken again the number 12 and we've partitioned it into 10 add 2, and then we multiply each component of that partition by the 3. So 3 times 10, or rather 10 times 3 is 30, and 2 times 3 is 6. We then simply add those two components together. 30 add 6 gives us 36. Again, we are moving on still further, but we're still using the notion of the method that's used in the grid, but we're simplifying it. And instead of drawing a formal grid, we start to just break down the calculation. So we say that 12 equals 10 add 2, and we multiply each of those parts by 3, and we create the calculation. 10 times 3 is 30, add 2 times 3 is 6, combined together gives us 36. And this then very quickly goes into a more short version. 10 times 3 gives us 30, and then we add to that 2 times 3 gives us the 36 in total. These gradually move into much more shortened versions. So we start to recognize now the place value, and that actually the number 12 is made up of a 2 in the ones column and a 1 in the tens column. So we can go back to using their digit value and their place value to ultimately make the calculation. So if we look here, we have 12 times 3. We can say that's 2 in the ones column times 3, which it gives us 6 in the ones column, and 1 times 3 in the tens column, which gives us 3 in the tens column. Here we are dealing with much smaller calculations, which makes the whole process so much easier. Now this will then move on to issues where the multiplication will go over the column boundaries between the different place values. So for example, if we look here, we change the number from 12 to 15, we now have 5 times 3, which gives us 15. Now we can't put 15 into the ones column, so we simply put 5 into the ones column, and then the 10 that we have remaining is transferred to the tens column as a 110, and is added then into the next calculation. And we have 1 in the tens column times 3, which is 3, add the 1 that we've carried from the previous calculation, now gives us 4 in the tens column. So our ultimate calculation, 15 times 3, comes out at 45. These various methods will take children a number of years to assimilate and to expand through. And alongside the 2-digit by 1-digit calculations, we will also be extending in the various methods to 3 digits by 2 digits, 4 digits by 2 digits, and so on. So we will end up with a compact multiplication method, which you can see here. Here we have 125 times 43, and using the distributive property of multiplication, we can break that down, and we can break it down using its place value as well. So for example, we start by making our multiplication by 40. To begin with, we put a 0 in the ones column. This tells us that we are multiplying by a number of tens. So the 10 part of the calculation is already done by placing a 0 in the ones column. We now only need to think about it as 4 lots. So we start by 5 in the ones column times 4, 2 in the tens column by 4, and 1 in the hundreds column by 4, adding in the various carries at the different stages. So that gives us our first line of 5,000. We then do our next line, which is the 3 in the ones column by the rest of that number. So again we have 5 in the ones column times 3, 2 in the tens column by 3, and 1 in the hundreds column by 3. The resulting number, 375, is added to the 5,000 we got from the previous part of the calculation, giving us an ultimate total of 5,375. So we are breaking the system down in stages. It's not simply a case of creating something that works and getting children to just copy it and practice and practice and practice, but trying to build their knowledge of multiplication so they understand the various processes. Now you might look at this and think, well, we didn't do grid method at school, and many of you, that's probably true. I certainly don't remember ever doing the grid method of multiplication in primary school. However, there are aspects of multiplication at later stages in mathematics, particularly when they start dealing with algebra, where the only really effective way of doing the multiplication is by grid method. So it's really important that children do get to grips with this method, and actually many children find the grid method something they really can focus on, and it becomes very clear that they are very confident and comfortable using the grid method. So much so that actually trying to move some of them off the grid method and onto the more compact methods can be problematical. I hope this short video has been of use to you and has given you some understanding of the different ways in which we teach multiplication in school. Neither one method is better than the other. They're all different methods, but they are intended to be a building on process, so that ultimately we want to get to the most compact and efficient method. But as often goes, children and adults will use different methods at different times, and that's fine, because the reality is that we all will have things that look logical one day in one way and other days will look logical in another way. That's fine. There is no right way, there is no wrong way. There are just different ways. Anyway, we'll have another look at a different kind of calculation on another occasion. In the meantime, go figure. Bye.